Welcome back, students. Welcome to Day-2 POC-II crash course. So I hope yesterday's concepts were crystal clear to you, because all the topics, whatever I am discussing, are very, very important examination point of view. Right. Okay. So once again, today also confirm your presence by typing or by giving POC in the chat, and also type the city from where you are joining. Okay. And also inform your friends, whoever are joining along with you, inform your friends that this session has been started. Okay, if you feel that they have not joined yet, so inform them that today's session has been started. Okay. Okay, keep posting in chat, no problem. Okay, students. And now coming to today's topic, we will be mainly focusing on reactions of benzene in today's session. Okay. So what are the typical reactions of benzene? Because you might have already written first sessional examinations, and by this time your teachers in every class, 3-4 classes, they might have told the same reactions, that is electrophilic substitution reactions. So the characteristic reactions for benzene or any aromatic compounds are electrophilic substitution reactions. Okay, so in today's class you will be learning why benzene type of compounds, they will undergo aromatic electrophilic substitution reactions. Okay, and how many types of reactions are there, right? And what are these reactions? Okay, and what is the mechanism involved in each reaction? So first I'll be discussing the general reaction mechanism, then I'll be explaining about the individual reactions. Okay, so if you learn the general mechanism, okay, just identify how to replace the groups. In that way you can easily learn other reactions also. So let's start today's session, and let me share my screen. Reactions of any molecules, it depends on the type of bonding. So now let us try to understand what type of bonds are present in benzene structure. So this is the structure of benzene. So from the structure you can easily make out that this benzene contains carbon-carbon double bonds and carbon-hydrogen single bonds. Even though I have given one of the Kekulé structure of benzene here, the original structure of benzene is closely resembling as that of the resonance hybrid structure, where all carbon-carbon bonds are double bonds in nature. Okay, so overall if you see, it contains carbon-carbon double bonds and carbon-hydrogen single bonds. So due to the presence of these carbon-carbon double bonds, the molecule is considered to be electron-rich species. The electrons which are available in the sigma bond will be very closely held between the carbon nuclei. That is why we say sigma bonds are stable and strong. Okay. But when it comes to pi bond, the electrons which are present in a pi bond are less loosely held between both the carbon nuclei. So due to the presence of these carbon-carbon double bonds, benzene is considered to be electron-rich species. Because it is electron-rich species, it can donate its electron pair to any species which is deficient of electrons. That means benzene, due to the presence of carbon-carbon double bonds, it acts as a site for the attack of electrophiles, because electrophiles are nothing but electron-deficient species. Among three different types of attacking reagents, that is electrophiles, nucleophiles, and free radicals, among these three types of attacking reagents, electrophiles are the attacking reagents on benzene, because benzene is electron-rich species. Hence, benzene undergo electrophilic reactions. Now the question is whether the benzene undergoes electrophilic substitution reaction or electrophilic addition reaction. Now let us clarify that. Let us first consider possibility of the addition reactions first. Okay. So here this is the structure of benzene. When we add a reagent such as XY, then the added reagent will be attacking the doubly bonded carbon atoms. So what happens here? Both the groups present in the reagent will be added across the double bond. Okay, so that is how we get corresponding addition product. So what happens during addition? One of the pi bond electrons will be utilized by the reagent to make a bond with the aromatic carbon. And that is how here we get an addition product. Now compare the addition product structure with the original benzene structure. Here benzene is having delocalization of electrons and it is obeying Huckel's rule, and that is why it is considered to be aromatic. Okay, but in case of the resulting addition product, here the molecule is cyclic but the conjugation is not maintained, and also so this cyclic cloud does not possess 4n plus 2 number of pi electrons. To meet with Huckel's rule criteria, this resulting addition product is lacking a pair of electrons. Okay, that means it is having only 4 pi electrons and thus it is not aromatic. Okay, so usually any compound will undergo reactions to attain stability. As a result of addition reaction, benzene is giving non-aromatic addition product. So non-aromatic compounds are less stable when compared with aromatic compounds. That means ultimately it is giving a product which is unstable when compared with the starting molecules. It is because of this reason benzene does not prefer addition reactions. As I have already discussed, the type of attacking groups are electrophiles. Now let us consider electrophilic substitution reactions in case of benzene. So let us say XY is the electrophilic reagent added. Now when we add this electrophilic reagent to benzene, this reagent undergoes dissociation and it results in the formation of X plus and Y minus ions. So here X plus let us consider as electrophiles. So in a substitution reaction, so X plus takes the position of H plus in the structure of benzene and thus it results in the formation of substituted benzene as the product. Now if you look at the resulting product here, upon electrophilic substitution, benzene is giving a product which is also aromatic in nature. That means even after electrophilic substitution, benzene, it preserves its aromaticity and results in the formation of stable product. It is because of this particular reason, benzene rejects addition reaction while it prefers only electrophilic substitution reactions. Dear students, I hope it is clear up to now. If you have any doubts, you can type in the chat. You can type your doubts in the chat. Alternatively, I'll give a WhatsApp group link in the chat and the same group link is available in the description of this video. If you are watching the replay of this particular live session, then you can join in that WhatsApp group and you can post your doubts there also at later stage. Now that you have learned why benzene undergoes electrophilic substitution reactions, now let me explain the general mechanism involved in electrophilic substitution reactions of benzene. Aromatic electrophilic substitution reactions of benzene, it involves 3 steps. Because it is an electrophilic substitution reaction, in the first step there will be formation of electrophile. Now in the second step, the pi electrons which are present in benzene ring system will be attacking the electrophile to form resonance stabilized carbocation. Later in the third stage, the resulting carbocation undergoes deprotonation and thus finally forms corresponding substituted benzene. Now let us deep dive into this mechanism step by step. So the first step is formation of electrophile. Let us consider YZ as the reagent. So this YZ in the first step, it undergoes dissociation. So the bonded pair of electrons which are present between Y and Z atoms will be moved towards Z. As a result of this heterolysis, there will be formation of Y plus and Z minus ions. So this Y plus, due to the electron deficiency, it is considered as electrophile. And Z minus, because it is an electron-rich species, it acts as base in the latter stage. Now in the second step, the generated electrophile reacts with benzene. Because benzene contains delocalization of pi electrons, due to this it is considered to be electron-rich species. So one of the doubly bonded electrons of benzene will be given to electrophile because benzene is an electron-rich species and electrophile is electron deficient. So this electrophile reagent, while making bond with benzene, it utilizes one of its pi bond. Let us number this benzene ring system for the convenience purpose. So by utilizing the double bond present at first position, Y plus, that is the electrophile, makes a bond at first carbon of the benzene ring system, due to which the second carbon of benzene, it becomes electron deficient and thus it attains positive charge. So as a result of attack of electrophile on benzene ring system, this is how there will be formation of carbocation. Now this carbocation has few more resonance structures and they are obtained by the delocalization of the available pi bonds. So you can see at third and fourth position there is a double bond. So this double bond at third position shifts to second position to remove the positive charge from the second position. As a result of which we get another resonance structure where there is a formation of a new double bond at second position. On the other hand, the fourth carbon atom, because of migration of this pi bonds, that becomes electron deficient and thus it attains positive charge. Again, here for this structure also, there is double bond at say fifth position. So upon migrating the double bond present at fifth position to fourth position, the positive charge from fourth carbon can be removed. And that is how a new double bond will be formed between 4 and 5 carbon atoms. In that case, the sixth carbon atom becomes electron deficient. And that is how the sixth carbon atom attains positive charge in the newly formed resonance structure. So this is how there will be formation of a carbocation which is stabilized by resonance. That means the resulting carbocation has 3 resonance structures. So this resulting carbocation is also known as benzenonium ion or arenium ion. If you observe the resonance structures of the resulting carbocation, in all these 3 structures, this hexagon ring is common, which is part of benzene structure. And in all the structures, the electrophile Y attacks at first position. Because of that reason, the first carbon is tetravalent. So from all these structures, you can also make out that these 2 double bonds present in the resulting carbocation migrates between 2 to 6 positions. The positive charge is also migrating over 3 alternative carbon atoms. That is second carbon in the first structure, fourth carbon in the second structure, and sixth carbon in the third structure. So by combining all these features, we can give the resonance hybrid structure like this. A hexagon ring, which is common in all these resonance structures, and also a dotted line is shown between 2 to 6 carbon atoms, which represents the pi bonds delocalization in all these 3 structures, and the positive charge in the middle of this hexagon ring system. So this is how the resulting resonance hybrid will be shown in case of benzenonium ion. Now once carbocation is formed, the next step is deprotonation. Because the carbocations or any charged species are highly unstable, they undergo deprotonation to form highly stable product. So here the first structure of the carbocation is considered. So this deprotonation step is facilitated by the action of base Z-. If you recollect, this is formed in the first step during electrophile generation. Okay. Z- because it is electron-rich species, it acts as base and it causes abstraction of proton from the resulting carbocation. So this hydrogen atom present at first position on the benzene ring system, it leaves the molecule without the bonded pair of electrons, and thus it forms HZ as one of the byproduct. So this pair of electron will be now transferred in the form of double bond between 1-2 positions to compensate the double bond present at second position. And that is how the resulting product monosubstituted benzene gets back its third pi bond. And that is how the molecule behaves as an aromatic compound. And as you know, aromatic compounds are stable. So that means benzene, even after substitution, it maintains its delocalization of electrons and thus forms aromatic compound which is stable. So in this mechanism, the second step, that is the formation of resonance stabilized carbocation, is considered to be a rate determining step. Because the entire rate of reaction, that means how fast monosubstituted benzene is formed in this particular reaction, it depends on how fast the carbocation is formed in the second step. So once carbocation forms, immediately the base will come into the picture and it causes abstraction of proton and facilitating the formation of the product. That means the entire rate of reaction, it depends on how fastly or how easily carbocation is formed in the second step. It is because of that reason this particular step is considered as rate determining step. So from this, I hope the general mechanism involved in electrophilic substitution reactions of benzene is clear for you. Now let us proceed with one by one reaction to the possible extent. So depending on the time, I'll be taking up these reactions. So before we proceed further, let me know if you have any doubts in the chat. You can type your doubts in your chat. So alternatively, you can also provide in the WhatsApp group. So please type if you have any doubts so that I'll answer them immediately. So as I mentioned earlier, general mechanism is may not be that much important examination point of view. Just if you learn general mechanism, it becomes easy for you to write the other reactions. Now let us try to learn the most important reaction, nitration of benzene. So the nitration of benzene also involves same steps as that of the general mechanism, whatever I explained. So now let us consider nitration. Let me share my screen. So the nitration of benzene involves 3 steps. The first step is formation of electrophile. So in this particular reaction, nitronium ion will be generated as electrophile. And in the next step, the formed electrophile will be reacting with benzene to form resonance stabilized carbocation. And later in the third step, deprotonation of this carbocation occurs to form nitrobenzene. Now let us consider this step by step. In the first step, nitric acid reacts with sulfuric acid. So upon reaction between these two acids, there will be generation of nitronium ion, bisulfate ion and water as the products. In this, the nitronium ion, because it is electron deficient, it acts as electrophile. So the bisulfate ion, that is HSO4 minus ion, which is formed in the first step, will be acting as base in the third step of this particular reaction mechanism. So once the electrophile, that is the nitronium ion, is generated in the first step, in the next step, this formed nitronium ion will be attacking on the benzene ring system to result in the formation of resonance stabilized carbocation. Now let us consider that step. So here the generated nitronium ion acts as electrophile and it attacks on the benzene ring system. Because nitronium ion is an electrophile, it utilizes one of the pi bond electrons of benzene to make a bond with the ring carbon atoms. And that is how nitro group is attached at the first position on the benzene ring system. Let us number this particular benzene ring for convenience purpose. Let us say now the nitro group is attacking on the first carbon atom utilizing the doubly bonded electrons present at first position. In that case, the second carbon, it becomes electron deficient, and that is how a positive charge will be generated on the second carbon. So on attack of nitronium ion onto the benzene ring system, it results in the formation of carbocation. Now this carbocation has several resonance structures. So how we can get those resonance structures? Let us see. Now in this structure, positive charge is present at second position. Now at third position, there is a double bond. So if you shift the doubly bonded electrons present at third position to the second position, then a new double bond will be obtained between 2 and 3 carbon atoms. And simultaneously, now the fourth carbon, it becomes electron deficient because the double bond is transferred to 2 and 3 positions. And it is because of that reason, fourth carbon attains positive charge in the newly formed resonance structure. We can draw one more resonance structure for this structure. So that is by transferring the double bond which is present at fifth position to the fourth position. If you shift the double bond present at fifth position to fourth position, then a new double bond will be obtained at fourth position. But at the same time, now at sixth position, there is deficient of electrons due to the migration of the double bond. And that is how this sixth carbon of benzene ring, it attains positive charge. And thus results in the formation of another resonance structures. So these are the three resonance structures possible for the resulting carbocation. This resulting carbocation is also known as benzenonium ion or arenium ion in case of electrophilic substitution reactions of benzene. So the resulting resonance structures are usually shown with double-sided arrows because one is obtained from the other and they will be always shown in brackets. So if you observe these three resulting resonance structures, we can make out two important points. The first carbon atom of this carbocation is tetravalent because it has nitro group on it. And the second important point is the two double bonds as well as positive charge on the ring carbon. These features are migrating between 2 to 6 carbon atoms in all these three resonance structures. By combining all these resonance structures, we can write its corresponding resonance hybrid like this. So we have drawn a cyclohexane ring with a tetravalent carbon at first position where nitro group is present on it. Okay, and delocalization of pi electrons are shown between 2 to 6 carbon atoms. And also you can see in the resonance structures at 2, 4 and 6th position, the positive charge is present. So to represent this delocalization of positive charge over these atoms, we will keep a positive sign in the center of this particular ring system. So this is how the resonance hybrid structure will be represented. In the third step, immediately the resulting carbocation undergoes deprotonation. So here the first resonance structure is considered. It undergoes deprotonation. So for this reaction to facilitate, bisulfate ions which are formed in the first step will be utilized. So these bisulfate ions causes abstraction of proton from the resulting resonance stabilized carbocation. So when these protons are transferred to bisulfate, it results in the formation of sulfuric acid as the byproduct. So the bonded pair of electrons which are present between hydrogen and carbon will be migrated in the form of double bond to compensate the positive charge present at second position. And that is how the third pi bond will be restored in the resulting structure, thus results in the formation of nitrobenzene as the product. So this is how nitration of benzene occurs in three steps. The first step is the generation of nitronium ion by the reaction between concentrated sulfuric acid and concentrated nitric acid. And in the second step, the resulting nitronium ion attacks benzene ring and thus results in the formation of resonance stabilized carbocation. And later in the third step, this carbocation undergo deprotonation by the action of bisulfite ions and results in the formation of nitrobenzene as the substituted product. So in this reaction, the second step, that is formation of resonance stabilized carbocation, is the rate determining step, because the overall rate of the reaction, that is how fast the nitrobenzene or the substituted product is formed, it depends on how fastly or how easily the carbocation is formed in this particular second step. It is because of this reason the formation of resonance stabilized carbocation step is considered to be rate determining step. So in addition to nitration of benzene, benzene undergo various other electrophilic substitution reactions. A few are given here. So benzene undergoes sulfonation in the presence of concentrated sulfuric acid, and it gives benzene sulfuric acid as the product. Upon halogenation, benzene gives halobenzene when it is treated with a combination of chlorine and ferric chloride. It also undergoes Friedel-Crafts alkylation reaction when a mixture containing alkyl halide and aluminum trichloride is treated with benzene. It results in the formation of alkyl benzene. Another reaction, Friedel-Crafts acylation reaction, where a mixture containing acyl chloride and alkyl chloride is allowed to react with benzene, which results in the formation of a ketone. So these are the few more examples for the electrophilic substitution reactions of benzene. So take a screenshot of this particular slide, students, because this single slide depicts all the 5 reactions of the benzene which are given in your syllabus: nitration, sulfonation, halogenation, Friedel-Crafts alkylation, and Friedel-Crafts acylation reactions. So if they ask in the examination what are the reactions of benzene, or give examples for reactions of benzene, so you can write all these reactions which are given in this slide. So students, now that you have learned the general mechanism involved in electrophilic substitution reactions, and also you have learned the nitration, the mechanism involved in the nitration reaction, and also you learned by this time all these 5 reactions. Okay. So as a quick summary, you can refer this particular table also. So here in the first column, I have given the reaction type, all 5 reactions: nitration, sulfonation, chlorination, and so on. And each reaction, what is the reagent used? For example, in nitration, we have seen it is the combination of concentrated nitric acid and concentrated sulfuric acid. Now from this, the electrophile generated is nitronium ion, that is NO2 plus ion. And the finally formed product is nitrobenzene. Okay, so in the reaction, that Y group becomes NO2 group here. Okay, so wherever Y is there, you will keep NO2 group in the general mechanism so that you can easily write. Okay, so sulfonation of benzene detailed video is already provided on the YouTube. Okay, so I have made a detailed video. So you can check that, okay, video, and I'll be giving that particular video link also in the description. Okay, so if you are watching the replay of this video at the later stage, you can watch that particular video for clarity. Okay, so while the remaining reactions I'll be explaining in this session. Okay, they are similar to the nitration reaction. So when it comes to chlorination of benzene, chlorine and ferric chloride is the reagent used. So from this, positively charged chloronium ion will be generated as electrophile. Okay, so the final product obtained is chlorobenzene. Okay, now when it comes to Friedel-Crafts alkylation reaction, so here alkyl chloride along with aluminum trichloride are used as the reagent, and from this alkyl group will be generated as the electrophile. So the formed alkyl cation will be attacking in the next step on the benzene ring system. Okay, that is how finally we will be getting alkyl benzene as the product. And now when it comes to Friedel-Crafts acylation reaction, here acyl chloride or COCl, okay, and aluminum trichloride are used as in combination. So from this acyl group, acylium group will be generated as electrophile. Okay, now this acylium group just attached to the benzene ring system. So that is how we get corresponding ketone. Okay, so the resulting product in this Friedel-Crafts acylation reaction will be having benzene ring system, but in addition to that, it consists of a specific functional group, that is keto group. That's why we call it as ketone instead of naming it as derivative of the benzene. Okay, unlike all other reactions. Okay, so students, you can take a quick screenshot of this. I will remove all these annotations. Once you learn general mechanism, just replace these Y groups wherever Y group is there in the general mechanism with these groups. Okay, so that you can write the mechanism for the specific reactions. You need not to every time prepare also. If you thoroughly prepare with one reaction, that reaction mechanism, that is more than enough. Just replacement of group. Only thing is you have to separately learn for the sulfonation, because it involves a 4th step. An additional step will be involved. Okay. So you can take screenshot of this particular slide and you can use this as a quick reference in your examinations. So students, I hope from this the nitration of benzene and the all 5 reactions are clear to you. So that table is important. If you learn that table, the 50% of the work is done. Okay, just you have to replace that Y group and you have to rewrite all the mechanisms. That is only pending. So you can try on your own also. Dear students, so in the general mechanism and nitration, I have given proper benzene ring structure along with the resonance structures, okay, for the resulting carbocation. So separately resonance structures and resonance hybrid structure, everything I have given. So those who are aiming for the A grade or O grade, of course, they have to learn all the resonance structures. But if your criteria is to just clear the subject, that is pass mark, and also be up to B grade, okay, so I will give you another alternative also that I will explain how to represent that when it comes to that I will explain by taking halogenation as an example. And also I'll be giving you some examination tips to achieve your desired grade. Okay, so what is your aim to pass this particular subject or to get A grade, B grade or O grade? Accordingly, I'll be giving you some of the important examination tips. So stay with me till the end of this video so that you can take a screenshot of those key takeaways also at the end of this particular live session. So I'll be giving again the clear mechanism for halogenation quickly here. And meanwhile, if you have any doubts, you can keep in the chat. So here chlorination of benzene is considered as an example under halogenation. So the reagent used in chlorination of benzene is a mixture of chlorine and ferric chloride. So when benzene is treated with a mixture containing chlorine and ferric chloride, then there will be formation of chlorobenzene as the substituted product with the formation of ferric chloride and HCl as byproducts. A positively charged chloronium ion will be generated from the mixture of chlorine and ferric chloride, and it is considered to be the electrophile in this reaction. Now let's see the mechanism involved in this chlorination of benzene. So halogenation of benzene, it involves 3 steps. In the first step, chlorine reacts with ferric chloride and it forms a complex. So how I have written the complex structure? So this is FeCl3 is written first. Now chlorine means Cl bonds with one chlorine bonds with another chlorine. So I have written that also. Okay. Ferric chloride is considered to be Lewis acid because of the presence of the empty orbital. So it will try to take up the electron cloud from the chlorine. Okay. That is why a bond is shown between iron and chlorine. Okay. Because now chlorine is going to lose its electron pair. It attains positive charge. Okay. And because iron is getting now the excess electron pair, we have given a negative symbol on that. Okay. So what we have written here is simply write ferric chloride and Cl2 like this. Okay. Keep positive charge on the chlorine of chlorine molecule. Okay. And negative charge on the iron of the ferric chloride. So this is how there will be formation of an ionic complex. Okay. Now the formed reagent complex, it reacts with benzene. So the same structure is given here. Okay. And it reacts with benzene. So when it reacts with benzene, out of C6H6, we have written C6H5 separately and H has shown here. Okay. So from this, the concept in the second step is the electrophile will be attacking on the benzene ring system. So in this, the electrophilic region is electron deficient region. That means the positively charged chlorine will be acting as electrophile. So that is the reason that positively charged chlorine attack we have shown in the product. Okay, due to which the carbon of the ring carbons of benzene, it gets positive charge. So that is why it is shown as C6H5H, which is from benzene, and chloronium ion attacks on one of the carbon of the benzene. So hence it is attached here. Okay, so thus it results in the formation of resonance stabilized carbocation. So here only one structure of the carbocation is given. So if you want to write all the 3 resonance structures, refer to the general mechanism and also nitration of benzene so that you can easily make out. So wherever that Y group is there or the NO2 group is there, there you have to keep chlorine. Okay, and the remaining part of the resonance structures are same among all the carbocations. Okay. Now, if you remove this positively charged chlorine, then what is left over in the reagent? FeCl3 and Cl. So, we attached this Cl here so that it becomes FeCl4 and negative sign is there on the iron. So, that is the reason same thing we will get here. Okay, that is FeCl4 minus ion we will get in this particular step. Okay, and as you are aware, this second step, that is formation of carbocation, is a rate determining step. Now, once carbocation forms, immediately the base, that is the negatively charged ion which is formed in the previous step, that is FeCl4 minus ion, will be acting as base and immediately it causes subtraction of proton. So it will take up this hydrogen from the carbocation. This bonded electrons will be given to the ring carbons to remove the positive charge. So that is how finally chlorobenzene, the corresponding substituted product, will be obtained. Okay. So this FeCl4 minus, it reacts with H plus and it forms HCl and ferric chloride as the byproducts. If you feel difficulty in writing the complex structure or attaching this complex to the benzene structure, I'll give you another alternative also. In that way also you can show the halogenation of benzene. So you can represent the mechanism like this also. First step, reaction occurs between chlorine and ferric chloride. So instead of showing complex reagent form, you can show that chlorine is already given to ferric chloride. So it becomes FeCl4 minus. Okay. And thus chloronium ion will be generated as the electrophile. Okay. Now the liberated chloronium ion, it attacks on benzene ring system in the second step. Okay. And it forms corresponding carbocation. And this step is the rate determining step. Okay. Now once carbocation is formed, immediately the action of base comes into the picture. This ferric tetrachloride ion which is formed in the first step acts as base and immediately it causes abstraction of proton. And that is how we get chlorobenzene as the main product and HCl and ferric chloride will be obtained as byproducts. If you feel difficulty in writing that complex structure, okay, and showing the attack of the positively charged chloronium ion, you can simplify like this also. So here for benzene, I have written the molecular formula. Instead of that, you can represent even the ring structure as I have shown in case of nitration of benzene. So in case of Friedel-Crafts alkylation reaction, the single line reaction is already considered. Now let us briefly, so here briefly I'll be explaining about the mechanism. It is similar to the nitration or the general mechanism involved in the benzene reaction. So first step, alkyl halide reacts with aluminum trichloride which acts as Lewis base. So it will take up the chlorine group. So it causes formation of alkyl cation. And this after taking the chlorine, aluminum trichloride, it becomes AlCl4 minus. Okay. So thus there will be formation of alkyl cation and aluminum tetrachloride anion as the base. R plus. So this formed alkyl cation acts as electrophile in the next step. So this formed aluminum tetrachloride anion will be acting as base in the third step. Okay. Now the formed alkyl cation, it attacks on the benzene ring system. Okay. And there will be formation of carbocation. So this is same as that of the halogenation which I discussed. Okay. Now once carbocation gets, immediately it reacts with the base. So that is the aluminum tetrachloride ion which is formed in the first step. And this one, a base causes subtraction of proton. So upon reaction with proton, this aluminum tetrachloride will be converted to aluminum trichloride and hydrochloric acid. Okay. Now if you remove this, the bonded pair will be supplied to the benzene ring system to remove the positive charge. And that is how here we will be getting C6H5R, which is nothing but alkyl benzene as the product. So here all these three steps are similar to that of the halogenation or the denitration of benzene. So in this reaction also, formation of the carbocation is the rate determining step. So how we have written the carbocation structure? So even in case of Friedel-Crafts acylation also, it follows the same mechanism. So first step involves reaction between acyl chloride and aluminum trichloride. And here also aluminum trichloride will be taking up the chloride. And that is how there will be formation of aluminum tetrachloride anion as the base, which acts in the third step. Okay, for the deprotonation. Okay. Now the remaining part, if you see, it becomes RCO. Okay, because this bonded pair is moved to chlorine. So the carbon becomes electron positive. So that is how there will be formation of RCO plus ion, which is nothing but the acylium ion. So this acylium ion, because it is electron deficient, it acts as electrophile. Okay, and it attacks on the benzene ring system in the second step. Now this step onwards, it is similar to that of the general mechanism. You can take screenshot of this. Okay, so there will be formation of resulting carbocation here also. The carbocation reacts with the base, and thus there will be formation of ketone at the end, along with the formation of aluminum trichloride and hydrochloric acid as the byproducts in this reaction. So the reaction mechanism, again, these three steps similar to that of nitration of benzene or sulfonation, other reactions which I discussed previously. You can take screenshot of this. So you can take screenshot of this and you can make it fair afterwards. Okay. So now students, I'll stop here. Now it's time for key takeaways of day 2, that is today's session. So what is mostly important, that means what you have to learn must and shouldly to get at least pass mark is why benzene undergoes electrophilic substitution reaction. Okay. So how benzene acts as electron rich center? It is due to the presence of availability of pi bonds. Okay. So that was first point. And second point, why? That means it becomes the site for the attack of electrophile because it is electron rich species. Okay. Now the second point is related to why only substitution. So that means you write one sentence related to why electrophiles attacks on benzene ring system and why only substitution occurs. Okay. So I have given an explanation, detailed explanation, but at least each one of you remember two sentences. One sentence related to why electrophile attacks, another sentence related to why only substitution but not addition. Okay. So that means we are giving the reason why electrophilic substitution reaction occurs for benzene. Okay. So only one or two sentences. Only thing is core point should be considered. That's it. Okay. So that is the most important thing that everyone should learn. And the second thing is, even though examination point of view, general mechanism is not important. But once you learn the general mechanism, as I have shown in the table also, you might have taken screenshot of that. If you are attending at the end of this particular live session, then go back to the replay and watch whatever I explained in the table. Okay, so wherever that Y is given, just replace with the electrophile in the specific reaction, so that it becomes easy for you to write the reaction. So that's why learn general mechanism also, even though it is not important, but because it serves as the model for the other reactions. Just by replacing Y with the specific electrophile, you can easily write other reactions. In fact, instead of learning everything like a new thing, it becomes practice for you also. Okay. Then must and shouldly you have to learn all the 5 examples. Okay. That means don't learn mechanisms in the first instant itself. Learn only single line reactions for all the 5 examples. So all these points are mandatory for any students because we know that it is a definite question. Okay. So I can't say whether you will get 5 marks, 10 marks or 2 marks question, but one question, definite question you will get from this particular topic, that is reactions of benzene. Okay. And then you learn one by one reaction. Okay. So because you now know the general mechanism involved, now implement that replacement Y group with nitro group, NO2 group in case of nitration. Okay. Again, try to learn the mechanism. Okay. So first always learn only the single line reaction. Okay. Then step by step mechanism, try to learn for the other reactions. Okay. Now, if your aim is to just pass the subject or up to B grade, then try with the benzene formula. Okay. As I have shown for the halogenation reaction. Okay. So in the general mechanism and nitration, I have shown benzene ring system and all the resonance structures with the delocalization of pi bonds, everything I have shown. No. So in that way, you need not to attempt. If you don't attempt in that way also, at least like as I have shown for the halogenation of benzene, in that format, if you prepare just with C6H6 by considering C6H6 as the benzene formula, also you can easily score up to B grade. Okay. Because there you need not to write the resonance structure. Okay. You will write only one carbocation structure. For example, when it comes to nitration, you can write the resulting carbocation structure like this. C6H5H, this is benzene. and NO2 group here. Because NO2 group is electron deficient, it takes the electron pair from the benzene ring system. So the carbon of the benzene rings becomes positive. So you will write the carbocation structure like this instead of giving the 3 resonance structures in the resonance hybrid formula. But with this format, you cannot expect O grade. That is for sure. But at least up to B grade, you can easily have it. Okay. Now, those who are aiming for A grade or O grade, try to give the mechanism as I explained, similar to that of the general mechanism and nitration of benzene. That's why two model types of the mechanisms I have given for different reactions. Okay. So that is must to get the A grade or O grade. Okay. So you just see what is your objective. You just see what is your end goal. Whether to just pass the subject, whether to get the B grade, C grade, A grade or O grade. Accordingly, you can attempt for this particular topic. Okay, because this is must topic. So you have to at least learn the first 3 points. Okay, they are very, very important. So students, if this session is useful to you and if I have given any value, that means at least a few useful tips for your examination, please subscribe my channel and also forward this particular replay or link to your friends also, so that they will also subscribe and they will also attend these live sessions from tomorrow onwards. Okay. And if you missed yesterday's session, as you are aware that these sessions are free live sessions on YouTube every day starting from 28th December till 12th of January, it will be there from 6 to 6:45 p.m. If you missed yesterday's session also, no problem. You can watch the replay. Okay, so replay is already available. So you can watch the replay. And you have any doubts, if you have any doubts, you can post in the chat. Okay, so because it is today's topic was little lengthy. So if you have any doubts related to this topic, you can share in the chat. Okay, alternatively, you can join on the WhatsApp group. The link is given already in the chart. Okay. And the link, if you are watching the replay, that link of the WhatsApp group will be available in the description. You can join in that group and you can also ask your doubts so that I can clarify. So thank you so much, students. Thanks for staying with me. And I hope you will revise. Okay. So take 15 to 20 minutes after this session, revise the topic, and very soon quiz will be enabled. Okay. So attempt a quiz also. And we'll meet in the tomorrow session. So in the tomorrow's class, I'll be discussing about theory of orientation and reactivity in monosubstituted benzene. Again, one of the definite examination question. Okay. So let us meet in tomorrow's class. Take care.